This is Amit Swain. I am a researcher at TCS Research. It's a great privilege to present our work here at IEEE Census 2022. So our work is titled Milliwear. Milliwear is a short-range InSAR approach for surface wear inspection using millimeter wave radar. This is a brief outline of the presentation. The problem I'll be speaking of is that of surface wear inspection through occlusion media. Now the question comes, in what scenarios do we need to inspect wear through occlusion? Let us imagine the scenario of an ore grinding mill. As you can see, the ore grinding mill is a huge mineral processing equipment, the interior of which is fitted with liners to protect its outer surface. Ore grinding process generates a lot of dust due to crushing and grinding of ore. Furthermore, the grinding of ore and the impact of the grinding media with the liners produces a wear on the surface of liners with time. This progressive wear needs to be measured in runtime. But as you can see, the ore grinding mill is just kind of a black box. The operators don't know what happens inside of a mill during operation, and the mill operates 24/7. Other possible areas are surface profiling in the presence of any kind of a protective coating or packaging. Wear is a serious problem for the industry. It is associated with unplanned maintenance, sudden machine breakdowns, and huge downtime costs. Next, let us have a look at some of the existing techniques for surface wear inspection. The state-of-the-art technique is laser scanning and contouring. So here you can see a LiDAR sensor taking a scan of the interior of a grinding mill. This can be used to detect the wear on the liners, but the shortcoming of this technique is that this requires the stoppage of operation of the mill. The next technique is via using a mechanical wear reading device. So this is a spot measurement, and it is kind of a manual technique where measurement has to be carried out at different wear zones manually. Coming to another technique, that is a vibration detection based approach. So here it is a passive wear inspection technique which gives us an idea of the anomalous vibration that is caused due to liner wear, but it won't be able to localize the exactly worn out liner in the grinding mill. Lastly, some of the X-ray based inspection techniques are also mentioned in literature. Now, coming to our approach, we propose to measure this surface wear using millimeter wave radars. Millimeter wave radars can see through dust and take radar measurements. These can then be used to reconstruct focused SAR images of the target scene. We also intend to perform active profiling of the in-situ surface wear and use short-range SAR interferometry technique to measure the surface deformation. The novelty of our research lies in the variable focusing framework for the RDA algorithm, which generates focused SAR images. Also, an automated anchor point based InSAR correlation scheme has been introduced for precise alignment of SAR images. Now, let us discuss the fundamentals of SAR imaging. SAR, or synthetic aperture radar, is a well-known remote sensing technique used for aerial and spaceborne surveys. It uses the motion of the platform on which the radar is mounted to reconstruct an image of the target scene. In this case, we are interested in a side-looking radar which scans in a strip map fashion and illuminates a wider swath. Using SAR image reconstruction algorithms, we can create a 2D complex image by combining the spatial resolution along the range and the cross range. Each point on this illuminated plane can uniquely be mapped to the time delay along the range dimension and the Doppler shift along the azimuth dimension in the image. Coming to millimeter wave SAR, millimeter waves are extremely sensitive to surface perturbations in metallic surfaces. When incident on a metallic surface, they induce a surface current density, and this is perturbed whenever there is a surface wear or defect, and it scatters the wave. The backscattered signal is then caught by the radar in motion. There are three key domains for SAR image reconstruction: range Doppler domain, wave number domain, and space-time domain. Let us now have a look at one of the image reconstruction algorithms that work in the range Doppler domain. RDA uses raw SAR data to perform range compression. Range compression involves performing a fast Fourier transform in the range dimension, followed by a match filter operation with respect to a reference transmitted signal and an inverse Fourier transform. After this, a Fourier transform is carried out in the azimuth dimension, followed by the migration correction, and followed by another match filter operation, which is carried out in the azimuth dimension. Then an inverse Fourier transform is done to generate the final compressed SAR image. This expression shows the reference function that has been taken for the range cell migration correction. Coming to our modification in the existing range Doppler algorithm for short range applications specifically, the conventional RDA considers phase correction by taking a single near range value. For satellite based SAR, this near range value is in hundreds of kilometers, and even with a single point, the focus SAR image can be constructed. This is, however, not true for short range applications. For short range applications, we introduce a concept of variable focusing, where we estimate the pulse width at the mid reference level of the fast time or the range waveform to compute the spread of the object along the range. This spread is then divided into multiple range windows, and the synthetic aperture length for each range window is calculated. Thus, we consider multiple focus points and try to reconstruct the image. So this is very relevant for short range imaging, where the slant range is in few centimeters. Here, variable focusing RDA generates much better focus images as compared to the conventional RDA. Interferometric SAR or InSAR generates topographic maps or images of the sample under test. In this image, you can see there are two SAR images which have been acquired from two different vantage points. In a repeat pass mode, this is carried out at two different time instances, T1 and T2. Let us consider the first SAR image being taken at time T1 when the sample was intact. At time T2, the sample had gone some degree of wear, and that becomes the slave image or the image taken at time T2. By conducting a complex multiplication of these two images, an interferogram is generated. An interferogram is essentially the phase of this complex product of the SAR images. Our contribution in the interferometric processing lies in the automated anchor point based co-registration. So in both the master and the slave image, we estimate anchor points based on the spread function of the object in the SAR image. Around these anchor points, a group of pixels are selected, and these are oversampled. After taking a 2D cross correlation, a fine level shift is estimated, and a coarse level shift is also estimated based on the difference of anchor points in the two images. This gives the net shift, and finally we can generate co-registered SAR images. From there, we can take a complex multiplication of both of them and generate the final interferogram. Let us now have a look at the experimental setup. You can see the radar sensor mounted on top of a conveyor belt and taking a scan of the sample under test. The radar used is Aconier A111 pulse coherent radar, which operates in the 57 to 64 GHz range, a bandwidth of 7 GHz and a center frequency of 60.5 GHz. It has a very fine range resolution of 0.5 mm and a narrow beam width of 17 degree along E plane and 15 degree along the H plane using the lens. It is mounted at a look angle of 30 degrees, and the conveyor belt is moved at a speed of 3 cm per second, and it traverses a total distance of 100 centimeters. It illuminates a swath of 10 centimeters on the sample. The sample chosen is an aluminum alloy plate, is a square plate of 15 centimeter cross 15 centimeter dimension, and impact wear has been created on the sample by hammering action. Here you can see a video of our lab scale millimeter wave SAR setup. This is the pulse coherent radar, which is scanning in a strip map fashion and illuminating a swath of 10 centimeter on this aluminum alloy sample. There is an impact wear at the middle of this area. In a similar manner, the radar scans once with an intact sample and once with a wear sample. The intact sample has been used as a master image and the worn out sample as a slave image for InSAR processing. After the data was collected from the lab scale setup, we execute the variable focusing RDA and generate the amplitude and phase images. Here you can see the amplitude and phase image of a normal or an intact sample. This sample has been used as the master image for interferometric processing later. You can see a rectangular region of around 10 centimeter swath and 15 centimeter along the azimuth. The next set of results show the SAR images captured for the master or the intact sample and the slave image of the worn out sample. Here you can also see the anchor points that have been estimated using the spread function along the range and the cross range of both the SAR images. Additionally, for the wear out sample, we can see a distinct perturbation in the amplitude image. And the same aligns with the position where there is a impact wear in the real sample. After the anchor points are estimated, the same are used to co-register these images and then move on to the interferometric processing. After co-registration of the master and slave images, a complex product of both of these images are taken, and the phase of this particular product or the interferometric phase generates the interferogram. In this interferogram, a region of interest is highlighted, which corresponds to the space where the sample was kept. The same is magnified, and here number of markings are made. So there is a reference marking with respect to which deformation has been calculated, and there are 5 different markings at different zones of the plate. The next step after the interferogram generation is the estimation of wear. The wear is estimated by observing the phase differences at the different point with respect to a reference in the interferogram. Here you can see in marking number 4 and 5, there has not been significant phase difference. It remains almost constant, and this corresponds to the area where there has not been any wear. For markings 1, 2, 3, so we can see there is a deformation and the respective wear has also been estimated. The ground truth wear in these points have been measured using a laser rangefinder, and we have estimated the squared error between the ground truth and the estimated wear. The mean squared error comes out to be around 0.0611. So we can see that the estimated measure or the measured wear is quite close to the ground truth measurement. Next, a few concluding remarks. Our approach leveraged off-the-shelf millimeter wave pulse coherent radars for conducting non-contact surface profiling in short range. It is extremely relevant for use cases as was discussed at the beginning of this presentation, where wear had to be inspected in situ in the challenging environment of a mineral processing equipment or grinding mills. It is also relevant for surface defect inspection through protective coatings as well as packaging. We discussed a unique variable focusing algorithm which could reconstruct focus SAR images even in short range, and also an automated anchor point based co-registration technique that is key for interferometric processing of the SAR images. The generated interferograms gave us a sub-millimeter precise measure of deformation that was caused due to the impact wear on our lab scale samples. We observed a strong overlap between the ground truth and our estimated deformation with a mean square error of 0.0611. In future, we look towards having a short range single pass based InSAR. So in this approach, we had used repeat pass InSAR. So we are looking also at single pass interferometric SAR, as well as compensation of phase errors that has been caused due to minute platform vibrations, and some of the more realistic surface wear scenarios like abrasive wear, impact wear, corrosive wear, different types of wear, and also moving from lab scale samples to field. With this, we come to the end of our presentation. If you wish to collaborate or have any queries regarding Milliwear, please feel free to contact via email.